Hello, my name is Brett Young, and I'm a former construction project manager, BIM consultant, and a current software developer. At M2X.ai, we help people reimagine project delivery as a product configuration experience. We're doing this for prefabricated timber panels, conference room audio-visual equipment, ductwork, and data centers. I was originally going to talk about productization in construction, which I think is really important for DFMA. But given the common interest we have in AI, I wanted to shift gears a bit and talk about my personal tech journey, how I have engaged with AI. AI is a really tough topic, and I hope I can help you imagine a future world where AI is important for construction. My personal tech journey began with AI with auto routing of piping through LiDAR data. The algorithms we used fell into the scholastic definition of AI, but when we went through and talked to people, we often got confusion because it didn't feel kind of AI enough. A venture capitalist even remarked one time, he goes, "How hard can pipe routing actually be? We don't think it is a tough enough problem that you're going through and solving." I thought we were solving a tough problem, but I took the opportunity to think about AI from a branding point of view or for like an optics point of view. And that kind of led to two great questions that went looking for answers. Question number one is, what is AI? And two, how can it be applied to construction? Now, the first question of what is AI is actually pretty difficult to go and kind of puzzle through. AI is a term that has been around for a long time. And to some, even today, it means self-driving cars. And to others, it may mean a rice cooker. Clearly, AI is about automation, but algorithms are also about automation, and they aren't AI. To answer the question of what is AI in my own way, I look to how we think of data mining compared to data querying, or the difference between data mining and the use of SQL, or structured query language, which I'm sure many of you may have a background in. SQL is a fundamental database technology, and it's used to create a question that you then get an answer for. You aggregate data and ask a question of a data set, and then you get back a collection of answers. Data mining is different from SQL because it finds correlations without directly structuring a question. And the best example of data mining is a example that came out of the early 1980s with a group at National Cash Register that was analyzing cash register transactions to understand how they could do better marketing. And what they were doing is, without looking they were looking at correlations kind of broadly, and they found a super high correlation in between diapers and beer. And you think about it, I get it. If you are buying diapers, you are not going out and buying beer at a restaurant or a bar. And so you need beer at home because you have diapers and presumably a child. And totally reasonable explanation for why you'd want both diapers and beer. But the cool thing was they didn't ask that question of all the data they had. The correlation came out on its own, and that is what data mining is about. You get an answer without asking a question. Bringing it back to AI and what it means to me and how I kind of have learned to engage it is that AI is the creation of algorithms that you can apply to anything, but you create those algorithms without writing algorithms. What you do is you use data and other techniques to automatically create, or not automatically, but create an algorithm that you can then go apply. So like data mining, it is a byproduct of not doing what you're trying to do. It is, you're getting an algorithm without writing an algorithm. My exploration of AI then kind of moved on to the examination of large CAD files for piping companies. And the theory was that we could use the pipe files to create very, very large data sets upon which we could do deep reinforced learning, which is a type of AI. We took that data and we turned it into a graph network. So all the fittings in the pipes were connected up into a node-edge relationship and assembled. And the result was, well, we got a bunch of really pretty pictures. The conclusion we kind of looked at, we found, was that if you look at the data set or you look at the graph, you get very repeatable patterns within the data. Different colors here represent different colors of different types of fittings, and the regularity of the patterns represents how they are different along the course of the pipe run. But the regularity of the patterns was very, very predictable. And the conclusion we came to was that algorithms without AI could power amazing automation. And that caused us to, again, rethink our original question of whether or not we need AI to go off and do automation. I was then on the internet one day and I ran across a crazy kid in London who had posted on Reddit. Brandon is passionate about machine learning, and he had used it to teach a drone how to fly itself. Then he taught an airplane how to fly and dodge missiles within a game. And then he taught Iron Man with ducted fans on his arms and legs to learn how to fly and be stable. And I thought, you know, that kid could be kind of fun to work with. And so we started a collaboration with Brandon to understand if deep reinforced learning could be used to solve the coordination of pipe networks. And it produced a very interesting result, and I'll let Brandon now explain.
By the way, in all these clips, you're watching the AI's actual behavior in the simulation. This project was a great success, and I finished it by creating a short YouTube video explaining it on my channel called Starksel. It was this video that caught the attention of Brett Young, who then reached out to me. He suggested that rather than using AI to further the violence of war, we could instead use it to help people by applying it to the mechanical industry. I was interested. Brett then debriefed me on the challenge of coordinating pipes, ducts and vents in such a way to reach the most efficient coordination for a corridor. By that, I mean the coordination in which the ceiling in a corridor is the highest. After a bit more conversation, we devised an AI that will control the position of each pipe and duct, and would then be punished for lowering the ceiling. After 12 hours of training and 1.2 million coordination iterations, the AI had learned to perfectly place the pipes and ducts such to let the corridor have the highest ceiling. Now, this didn't take a large expensive team of people to do, just one student and one entrepreneur. With this in mind, I want you to imagine the sheer number of challenges in the mechanical industry that can be solved by dedicated construction technologists, BIM experts, IT specialists, and all other ambitious workers, and most importantly, yourself, with the use of machine learning.
The conclusion for that work was that we needed better algorithms for routing of pipes in 3D, which could then be driven by AI. So we put that project back on the back burner and waited for the development of those algorithms, and happened along on this tech journey. The conclusion we came to was that we needed better algorithms for routing pipes within 3D, and which could then be driven by AI. So we put that project on the back burner and continued on. I was then in Australia for a BIM conference, and I found a client who was interested in automating estimating. He asked if we could use AI to count fire alarm symbols on drawings, and we said we'd give it a go. We used Amazon to create a learning algorithm that could identify different symbols. it looked like a CAPTCHA test for logging into a bank account. Here again, we ran into a learning curve. The original setup we had was a little bit too complicated and needed to be simplified. But here again, we found that computer vision without AI was an effective strategy for doing takeoffs for estimating. It was a great conclusion, but clearly not, down the path of understanding how AI could be applied to construction. But it led to a very, very exciting place, which I want to tell you about. I want to talk to you about RFIs. RFI, request for information, everybody does them. And I find it really ironic that our industry has 100 different RFI management tools, but shockingly few, if any, tools for preventing RFIs. Here's a picture of me back when I used to write a lot of RFIs. I was a project engineer for a large general contractor. And my dream back then, and probably now, is that an AI could write the RFIs automatically. Why don't we jargon that up a little bit and not call it project engineer, but why don't we call it predictive analytics for project details? Now, this is a shockingly difficult topic for kind of a funny reason. When I was doing algorithmic PDF counting, a client asked me the hardest thing to do a takeoff of. And my answer at the time was, the hardest thing to do a takeoff on is something that isn't in the drawings because you can't count it. And to describe how this is related to RFIs and AI, my example is with rabbits and turtles. There are two related statements that you want to try and prove correct. The first one is, there is a rabbit in the woods. Now, if you go off in the woods to prove the statement, there is a rabbit in the woods, you only need to find one rabbit. The other statement that you want to try and prove is, there are no turtles in the woods. To go and prove that statement, you have to go and look under every log, every pile of leaves, and behind every corner to go and look for a turtle to confirm that there are no turtles in the woods. And it is a much harder and higher obstacle to get over, and is a part of it's actually has a legal term to it. Proving a negative is incredibly difficult, and is actually a background for the US Constitution and the idea that you're innocent until proven guilty. If you're innocent, you can't actually prove that you're innocent, because like the turtle, you have to go and look for under every log to prove that you that you're not guilty. This is all related to RFIs, because the most common type of RFI is one that asks for a detail or for a piece of equipment that isn't in the drawings. My favorite example is something called a condensate pump. A condensate pump goes below a mechanical unit that does cooling, and when the water comes off of the unit, it pumps the water into a drain. And the condensate pump itself is not much bigger or different than a fish tank pump, and is only a little bit more expensive probably than a fish tank pump, unless you do it through a change order. If you forget to specify a condensate pump, you get presented with a change order that tells you that you need electrical, you need routing to a drain that may not be there, you need a drip pan for the unit, and you have to do it, in addition to all your other work. And the change order is shockingly high. If you would have specified it ahead of time, it would be part of the project cost and planned for, and not nearly as expensive. But if you wanted to create an algorithm, for example, where you processed all the project files to examine whether or not a condensate pump had been specified in the drawings, like a turtle in the woods, you have to look through a shockingly large amount of data. You have to go through the drawings, you have to go through the specification, you have to go through all the previous RFIs, and And a lot of times, as a former general contractor, I would identify that the condensate pumps weren't in the drawings, and I'd write it into the contract for the bidder to pick up, even though it wasn't shown. So in addition, I also have to go through a subcontract log to confirm that a condensate pump isn't included as part of the project. And so if you abstract that away and go, I want to be able to mitigate the risk of any RFI for a thing not shown or a detail not shown, you get into a turtle in the woods type of problem where you have to go through and do a lot of data. And the problem is that in kind of the old way of doing things, we would write an algorithm to go, hey, algorithm, go and look for whether or not I have a condensate pump. And you'd tell it to go and look in very specific ways. But to me, this might be the perfect place for how AI could really help what we go and do. If I have a algorithm that can view PDFs and go through and look for symbols, and I have a tool that can go through and scan a repository of data, I can actually process a large amount of data and begin to think about it. Now, I want to talk a little bit about computer vision and how I think it plays into this kind of example of looking for items that aren't on the drawing. Computer vision is a lot like Photoshop. In Photoshop, or Instagram for that matter. In Photoshop, you can apply a filter to a photo and make it look a little bit different. In computer vision, you do the same thing, but you can apply lots of different filters in lots of different ways and stack them on top of each other and process them in different ways. You can come up with an insight and a pattern that then results in a conclusion that there isn't something shown. And because images are very memory intensive. A JPEG is a special type of array, but roughly you can think of it as one pixel being one color. And if there's a million colors and you have a JPEG that is, of a high resolution, that is a very difficult thing to go and algorithmically work with. And the reason you use filters is you can filter them down to remove colors and group colors. And then you're only talking about the center of a large block of color. And that type of approach has proven to show that you can find a correlation to identify a given object. Here's an example with the back of a car. The taillights are a very predictable large block of color, and the license plate is always in between them, or generally in between them in 2D or 3D. Another example would be a traffic light. A traffic light occurs off the road and has predictable colors and generally a predictable shape. So computer vision is used with lots of filters to find these types of patterns. AI applied to computer vision is letting the computer pick which order you apply the filters and which patterns to look for. You may have heard of a neural net. A neural net is that layering. Back to the RFI problem, we can use AI to decide how to look for a condensate pump or any other potential RFI. If you have a large repository of PDFs and a large repository of RFIs, you can use computer vision and a neural net to find the correlations that you know exist, but you don't want to discretely write an algorithm to go and find. You don't want to write 1,000 or 10,000 find my condensate pump algorithms. You want to use AI to be able to find all of that type of problem within your project. Pretty cool, right? The goal isn't to automate the work of a project engineer. The goal is to rethink how we describe the phase of a drawing set. A design development drawing set means different things to different people on different projects. But an AI that can automatically create a predicted design checklist, which would eliminate RFIs, would be very useful. And knowing how developed a set of drawings would be like an automatic level of development tool. Once you've tackled that problem, you can then tackle the bigger problem of automating the details that need to be created as part of the design. This is a tougher problem, but like the pipe networks and their predictability, buildings are actually fairly predictable and not an insurmountable problem because we have a vast history of what details look like and can create an understanding, a semantic reason for why they occur. The problem is really just not having enough people within our industry. The problem we're solving is that we never have enough people or time on a project to do all the checking that we want to go and do. So the core value of AI within construction is being able to make people better by taking this type of task, which is very, very manual and time consuming, and automating it with AI to create an algorithm without having to write an algorithm. So thank you for coming to my talk and going through what I had to say. I look forward to your questions, and I hope we can talk more about this very tough but exciting topic.